Hi everyone. So yeah, we had a lot of great talks today. I think it was really good combination of like this covering various aspects of efficiency. Like what enabled first the recent advancements of deep learning was kind of data, hardware, and algorithms coming together. And so yeah, we heard a lot about the hardware, and so I kind of want to talk about the AI part. So yeah, as Alexi mentioned, I'm a senior research scientist at NVIDIA, and I just want to present some of the works we've been doing on applying AI for actual problems in science. So just to kind of get a sense of the audience, did anyone hear of neural operators before? Cool. Oh, nice. Did anyone try neural operators in any project or? Cool. So I guess hopefully everyone can get something from the talk. So yeah, essentially the starting point is that a lot of phenomena that we're interested in are modeled by continuum equations, known or not. For example, Navier-Stokes equations, which describe the motion of viscous liquids, and the solution of these equations are functions. So we typically, for example, have the state of the physical system at a time t, and we want to describe how it will look like at time t+1. And so, yeah, we may have discrete observations to learn from, but really we want to learn what happens at the continuum. And so as a motivating example, I kind of want to take the example of weather forecasting, where we have the state, how the weather looks like globally right now, and we want to look at how it will be in an hour, 6 hours, maybe a week from now. And the key thing is that often it's not sufficient to just do a prediction. We also want to do probability. So if you look at weather, for example, as you, I'm sure all well know, weather forecasting is not super accurate. And so what we want to look at is ensembling, like what is the probability of a certain event happening? And this is especially true if you look at extreme events like a hurricane, and you want to know what will be the trajectory of this hurricane and so on and so forth. And it's also a really interesting problem for us because we were just talking about distributed training. Well, this is really relevant here because the scale is huge. So weather happens at multiple scales. And so, for example, if you want to resolve things like convection, you need to look at maybe a 25-kilometer scale. If you want to resolve storms accurately, you need to have a much more detailed state. So that would be maybe 1 kilometer. And then if you want to resolve clouds and have more accurate prediction, you want to go to 100 meters scale. Ideally, eventually, we'd want to go to 1 meter scale. The issue is that, of course, this is not a sustainable growth of compute, and it's completely out of reach right now. And both in terms of compute and storage, actually, there would be petabytes of data to handle. So even right now, if we want to train, right now we're at more or less 25 to 1 kilometer scale, both for numerical solvers and AI-driven models. And so already this requires actually distributing models on hundreds of GPUs and kind of, using these latest models. So this is where neural operators come in. Traditionally, neural operators, neural networks, regular neural networks, work on inputs and outputs at fixed resolution. For example, you have an image-to-image problem, you take your units, you train at fixed resolution, and you predict at this fixed resolution. But once you've trained your model, you cannot do inference, or you cannot easily retrain at a different resolution. You could maybe upsample, but you cannot lose all the new information. And so the idea of neural operators is to actually generalize neural networks to, instead of doing mapping between finite dimensional spaces, doing mapping between functions. So you take as input now a function, and you output a function, and you learn an operator to map between these function spaces. And so if you have this, you can now query at any point in the domain. And one property we want to have is what we call this discretization convergence, which means, like, for example, here, if you have an airfoil and you have an airflow around it, as you refine your mesh, you want the operator you're learning to converge to the same solution. You don't want to get a different solution at each resolution. And so kind of to summarize the properties we want of a neural operator, so the first thing, as I mentioned, is we want to learn a solution operator that maps between functions. We want to decouple the resolution and number of parameters. which means that you want to be able to train the same model on different resolutions without increasing the number of parameters. And you would want the solution to stay coherent between these different resolutions. And then once you have a model, you want to be able to fine-tune it or inference it at a different resolution. And finally, you want to be able to query at any points. So the framework in which we do this is called the neural operators. And the idea is that in deep neural networks, we use linear mappings, for example, convolutions of fully connected layers, which are followed by normalization, nonlinearities, etc. And you stack these layers, you build these deep neural networks, and you learn a mapping from your input to your output. The idea here is the same, except we use integral linear operator, which are frequently used in approximation theory, and that kind of map, they are linear mapping from one function to another function. So I kind of want to subdivide then the rest of the talk in multiple use cases depending on the geometry of your problem. So the first case is if you have a regular grid, say for example a 2D or 3D image or something on a 2D domain. And in that case, you can use the fast Fourier transpose, which will make things very efficient. So the idea is you take your kernel integral at the top, and we look at a specific case of the kernel integral, which is the convolution operator. So instead of having a general kernel so V here is your input function. So you're mapping your input function V of y to a new function that you will query at point X here. So you integrate your input function with some kernel, and here we simplify the kernel to just be a convolution. And so you may know that you can realize this efficiently with the Fourier transform. You take the Fourier transform of your kernel, the Fourier transform of your input function, and then the convolution simply becomes a pointwise multiplication in the spectral domain. And the advantage of this is you can, if you have a regular input, you can do this very efficiently with the fast Fourier transform. I don't know why I keep saying transpose. Maybe I blame the previous talk. And so, yeah, so now basically, instead of having a O of n squared complexity, you can have an O of n log n, which is much more efficient. And so in this case, the architecture will look very similar to a regular deep neural network, except now we have these neural operator blocks. So you have your Fourier layer, which take in your function, you transform it into the spectral domain. There you truncate the high frequency to remove the noise and kind of have something to have a fixed number of bases. You do your pointwise operation, you multiply by your weights, which here model your kernel, and then you do an inverse transform to get back into the original domain. And you stack a bunch of these layers with some nonlinearities in the middle to learn a mapping between your functions. And so the advantage is that now you can, here for example, I'm showing some examples on a Navier-Stokes problem, so fluid dynamics, and we trained our neural operator, our Fourier neural operator, on 64 by 64 resolution, but we can test it directly on 256 by 256 resolution without any retraining. And the nice thing is that you could say, okay, I can train my neural network, a regular neural network at a small resolution and just interpolate. But if you do this, your neural network has never seen the high frequency information you had. And so as you can see on the right, I guess you can't see maybe you can see the cursor. So if you look at the energy spectrum, on the left, these are the low frequencies, so you can learn them well because you've seen them during training. But on the right, these are wave numbers that were not seen during training. And so if you now use interpolation, your neural network kind of behaves erratically because it doesn't know what to do with the new frequencies, while the neural operator kind of generalizes well to unseen frequencies. So for anyone that knows me, I really like tensor methods. I worked a lot on them, so I couldn't do a talk without mentioning tensor methods. So they're still relevant here. Essentially, the core idea is that a lot of the data we manipulate in modern machine learning is high dimensional. And so by considering this structure in the data, and so considering the data as multi-dimensional array, we can extract more from it. And so the idea is very simple. So a matrix is just, let's say, a 2D array of number. You can think of a tensor as an n-dimensional array of numbers. And then instead of doing matrix multiplication, you do tensor contraction. So you multiply, for example, here a matrix with a tensor. And when you have this, you can generalize known concepts like matrix decomposition. So here, you can express a matrix as a a sum of rank 1 matrices, so a sum of outer products of vectors. And you can generalize this to tensors by expressing them as a sum of rank 1 tensors, which is the sum of outer products of 3 or more vectors. And so you have many kinds of tensor decompositions. And they're very relevant here because we have global convolutions. So they are parameterizing a convolution over your entire input. So they have kind of size, heights by width, by maybe time, by input channels, by output channels. So you already have a huge tensor. And so by expressing them in factorized forms, you can drastically reduce the number of parameters. So in the Fourier neural operator I presented before, we applied this idea, and we factorize the weights in the spectral domain. So we express them as a tensor factorization, and then during the forward pass, you can directly multiply your activation with the factors of the decomposition. And so essentially, we're able to improve the performance of the model with just a fraction of the model. So the one on the right was the original Fourier neural operator. In the middle, we actually just brought some existing known techniques from deep learning to neural operator realm, like properly doing things, normalization, etc. And then at the bottom is the tensorized version. So we have better performance with a fraction of the parameters, because these tensor factorization kind of act as a regularizer on the method, on the model, so you can learn more efficiently. So yeah, we're able to compress up to, let's say, 500 times without any loss of performance. And if you decide to just trim your model instead of using factorization, performance decreases very quickly. So it is a really principled way to do this compression. And it also helps in the low data regime. So actually, if you have less training samples, tensorization helps you to prevent overfitting. So anyway, that was a quick parenthesis on how we can bring tensor methods to this. And I want to go to the next use case, which is now if your domain is still kind of regular, but instead of being on a regular 2D grid, we're now learning on a sphere. And so this is the weather case I was presenting earlier. So here we're trained on some, the essentially gold standard of weather forecasting. It's called ERA 5. It's a reanalysis data. It has several decades of data. It's a 25 kilometer scale, and yeah, that's essentially the base data we kind of have for training now. And so there, the idea is exactly the same as the Fourier neural operator, except now our data is on a sphere. So we want to use this, and instead of doing a Fourier transform, we can now do a spherical harmonics transform. And so instead of having sine and cosine as the basis functions, because now we're representing a function, so the basis of our space are also function, we use spherical harmonics, so circular functions on the sphere. And so this is a very natural way to represent things on the sphere. And as you can see on the left, we have a transformer-based model that actually does very well at the beginning. But if you do autoregressive inference, so it means you take your forecast, let's say you're predicting the weather 6 hours from now. You take your forecast and you refeed it to your model to get a prediction for 12 hours. And as you unroll your model, you quickly get these weird patterns that essentially you can see the patching that the model was doing. While the spherical harmonics-based model, because it encodes the geometry of the problem, is able to do prediction on hundreds of days without going completely crazy. So yeah, and the advantage of our model is that it more or less matches the accuracy of current numerical solver of like weather forecasting models, but it is a lot faster. So here, like 45,000 times faster. And so this is really crucial if we want to do things like ensembling. And for example, this is the Hurricane Harvey in 2017. And this is, we can see the actual trajectory of the hurricane versus what was predicted. And so the issue is if you just look at one prediction, you will get something that's typically very wrong. There's a chaotic part in the system, so you can't really well predict it. So what we would want instead is to run our models many times, like thousands of times, and then build an ensemble of possible trajectories. And so from these, we can now not only have a predicted trajectory, but also the probability of it happening in different places. And so concretely, for example, right now the models are really slow. They take minutes to run, while our models run in milliseconds. So you can run thousands of ensembles much faster. And so this allows you to, here on the left, if you have only 50 ensemble, maybe you will only capture the kind of, you always have a sort of Gaussian distribution. So here it's like only a small range of wind speeds. And you need many more ensembles to actually be able to model the on the tails of the distribution, so the extreme winds. And so these are actually the ones we're most interested in predictive, because this could be the most destructive, or those we couldn't prepare for because we didn't have these trajectories. Cool. And so the last thing I want to talk is if you don't have any structure at all in your data. So previously we were doing nice fluid dynamics on the torus, everything was regular. Even for weather, it's all nice on a sphere. But there are cases where we just have arbitrary geometries and we still want to be able to solve things. So one case is aerodynamic simulation. So for example, if you have a car geometry and you want to predict the pressure on the surface of the car, or more generally the drag of your car. Ideally, if you're designing a car, you would like to be able to play with the geometry and then know how this affects the drag without having to stick your car in a wind tunnel or without having to wait a few hours for your simulation to run. And so this is a use case where it would be useful to have a surrogate model, an AI surrogate model that can do this efficiently. And so this is the idea of the graph neural operator. And the idea here is to be able to have a model we can query at any point and that can work at different levels of discretization. So you can now take your car and give this point cloud as input to your model at different discretization and get the prediction at any point. So this idea of sort of discretization convergence can be really useful. If you don't have that much compute, then you can start training at a coarse resolution and give few samples at high resolution as you get it. So this saves you like data and compute. And so the idea is once again based on this linear kernel integral, except now you have your function still v of x, the same as before, but now you have a query point. So let's say you want to query, for example, the pressure at one point on the surface of the car. You now build a neighborhood, so a ball around this point, and you integrate simply in the ball, so all the points around all the neighbors of this query point. And so you do your kernel integral only in this neighborhood. And the size of this neighborhood remains the same regardless of the discretization of your car. And so the idea of the whole model, which here we call GENO, was first, you have a GNO layer that takes your arbitrary geometry. You query it on a regular grid. So you have an arbitrary geometry. You query it on a regular grid. So now you can use your FNO, which is very computationally efficient because it relies on FFT. And at the end, you have another GNO layer to kind of decode your representation, and which you can query at any point. So then you can, again, query your model on all the points on the surface of the car, predict the pressure, and then from this predict the drag. So these are just some visualization of the pressure on the surface of the car. You can see the ground truth versus the predicted pressure. The error is quite low. And we found that we can get results with about 26,000 speedup over GPU-based optimized like fluid dynamic solvers. And so this is just to visualize this speedup. You can see in red and orange is this model. And this is a cost trade-off accuracy. So you can see the time. So it's basically the error in the drag, the car drag, as a function of time. And you can see that with our model, you can get as good an accuracy as the open foam solver, which is GPU accelerated, in much less time. So actually, this is all from me. So just to summarize, I think, this AI for science is really an exciting application of deep learning, and it really takes everything we've learned before, whether it's like how to build the architecture, how to scale the models, how to use very large amounts of data and kind of applies it to really real-world problem, which is really interesting. And neural operators are a really principled way to do this. So yeah, I hope you guys are interested in trying it. And because Alexei mentioned this is an open source only conference, everything is open source. And actually, it all uses PyTorch as well. So the neural operator library just provides layers and models to run these in PyTorch. And TensorLib provides all the tools to kind of manipulate factorized tensors as regular PyTorch tensors. And Torch harmonics is a library that just provides a PyTorch differentiable spherical harmonics transform. So great, that's all from me. Thank you very much. And if you have any questions, maybe
questions? Anybody have a question?
Yeah, thank you. That was great. You showed us towards the end that if you already know the geometry, you can figure out what the basis transformation needs to be so that you can do the operator. What if you don't know the geometry? Can you optimize the basis transformation just having like a pile of data?
That's a really good question. I guess the most general way would be this graph neural operator that I presented at the end. Then you just take any geometry and you're literally just learning the kernel. So that would be the most general. Otherwise, you could also try to parameterize this kernel by another network. For example, you could have an MLP. I'm sure you're familiar with NERF, for example, like implicit representation. You could have a model that takes as input your coordinates x, y, and it kind of maps them to the corresponding kernel. So there are all sorts of tricks possible. But the key thing here is that the FFT is really efficient. You can do it in n log n, and that's the main reason we use it. So you totally can learn the basis, but it would be harder, and you wouldn't get the speed up. And also, the key insight here is that whenever you have expert knowledge, I think it's always good to use it. It's like additional inductive bias. That's why convolutional neural networks work well on images. And I think, yeah, it's the same on every problem.
Okay, if not, thank you again.
Thank you.